Hi guys, welcome to Integral Calculus. In Integral Calculus, we're going to answer the opposite question that you guys asked in Differential Calculus. So what do I mean by that? In Differential Calculus, you started with a distance function, and from that distance function, you developed the instantaneous velocity. You call that the derivative. In this course, we're going to start with the velocity and try to find out how far we travel. And we'll see that this has many more implications than answering the initial question. So let's start out with an example so we can start wrapping our mind around how we would do that and what are some of the issues involved. Well, let's say I tell you that you're going 30 miles per hour, and I say that you do this for 2 hours. So my velocity function in this case is v of t equals 30. How far do you travel? Well, we could just look at the units and we could see that I can just divide these guys to get 30 times 2, or 60 miles total. So how did I get that? I took the velocity and I multiplied it by the change in time. So this is delta t, or change in time. So why do we need calculus? Well, what happens if your velocity is changing over time? What if at every instant you're speeding up, for example? We're not going to be able to play this same game. So let's think about an approach and then we'll work out the details. Well, let's say you go from 0 miles per hour to 60 miles per hour in 1 hour. So you're going from 0 to 60. Well, again, the problem is I'm speeding up throughout the entire hour. So what I could do is I could break this hour into 2 subintervals, namely from 0 to 30 and from 30 to 60. I could then pick one velocity to represent the velocity that I use over this time frame, then multiply it by 1/2, because I'm multiplying by a half hour. I can pick one velocity that I'm going in this time frame, again multiply it by a half, and then I can add these two guys up. That would then give me an approximation for the total distance traveled. All right, so I want you to stop the video for a second and ask yourself, how can I get a better approximation? Well, hopefully you said, instead of going from 0 to 30 and picking one velocity, which is changing throughout, and 30 to 60 picking one velocity, what you could do is you could break this into 4 subintervals, or 8 subintervals, or 100, or 1,000,000. In fact, the greater number of subintervals that you have, the better your approximation is going to be. In fact, mathematically, what we're going to do is we're going to take the limit as the number of subintervals approaches infinity. And we'll add up all of these distances to get what we're going to call the total distance traveled. So that's just a big picture discussion of what we're going to do. Now I'd actually like to work out an example where you have those ideas in your mind. So let's work out a specific example. So let's say I give you a table of times and velocities. And let's say this is hours, and this is miles per hour. So I don't know, maybe this is your grandma driving in a car. She's going 16 miles per hour by the time she hits 4 hours. Our goal is to come up with an approximation for the total distance traveled. So what I'm going to do is, first I'm going to come up with what I'm going to call a bad underestimate, and then we'll get a better underestimate, and then we'll do the same thing with an overestimate as well. So let me do a bad underestimate. So it's going to be bad because I'm not going to use all of the information that I have. Now note, I just have the velocities at these times. I don't know what's happening in between. But what I'll do is for my bad underestimate, I'm going to break these 4 hours into 2 subintervals. And then I'm going to use an approximate velocity on each given subinterval. So if you look at this car, it looks like it's speeding up. So for the first 2 hours, if I want the worst case scenario underestimate, what velocity should I use? Hopefully you said 0 miles per hour. So I'm going to say 0 miles per hour for 2 hours, and that'll be my approximate distance traveled. Again, not a very good approximation. For the second 2 hours, I want an underestimate, so I'm going to use the 4 miles per hour. And now I'll say I'm doing that for 2 hours. I can add these guys together, and I get an approximation of 8 miles. So I invite you to pause the video and see if you can come up with a bad overestimate mimicking the process above. Well, hopefully you said for the first 2 hours you'll go 4 miles per hour for 2 hours. Then for the next 2 hours you'll go 16 miles per hour. So here we have 32 plus 8, which is 40 miles. All right, so this is my bad underestimate. This is my bad overestimate. This tells me, though, that the true distance traveled is somewhere in between my 8 and my 40. All right, so let's now come up with a better underestimate. Now we want a better underestimate. So how are we going to do that? Well, by the initial discussion, we're just going to use more subintervals. So let's use 4 subintervals. Well, if I do that, sorry, let me get this out of the way. So 8, less than the distance, less than 40. If I use 4 subintervals, then for that first subinterval, I'll say I'm going 0 miles per hour. And I'm going to do that for 1 hour. Then, from 1 to 2, I'm going to say I'm going 1 mile per hour. Again, for 1 hour. From 2 to 3, I'm going to say I'm going 4 miles per hour for 1 hour. And then from 3 to 4, I'm going to say that I'm going 9 miles per hour for 1 hour. So let's add all these guys up. So this is 0 plus 1 plus 4 is 5 plus 9 is 14 miles. That shouldn't surprise you that the 14 is bigger than 8 because 8 was giving us kind of our bottom estimate. At this point, I invite you to pause the video and come up with a better overestimate. Well, hopefully you said for the first hour, you're going to go 1 mile per hour. Over the next hour, you're going to go 4 miles per hour. Over the next hour, you're going to go 9 miles per hour. And for that final hour, you're going to say that you're going 16 miles per hour. So 16 plus 4 is 20, plus 10 is 30. So we get 30 miles. So now we have a bound. 14 is less than the total distance, which is less than 30. So again, this shouldn't surprise you that these guys are mushing in. They're getting closer and closer because we have more information. And in fact, if you think about it, it shouldn't be unbelievable, or hopefully it makes intuitive sense that as the number of intervals approaches infinity, the number of subintervals approaches infinity, that those numbers are going to smush in closer and closer and closer to the true distance. All right, well, that's great. We found this, and this was a kind of a numeric example. Thinking back to calculus, differential calculus, when you guys first computed derivatives, you also explored the instantaneous velocity in a graphical sense. And you found out that, oh wow, this is the slope of the tangent line and lots of other goodies. So I want to see if I can visualize this process and see if I learn something additional from what's going on here. So I want to have a visual representation of these numbers. So I'm going to erase a bunch of things that we don't need right now, just to make it a little clearer. So we don't need this. I'm going to get rid of my units. I think it'll just clog up the point. So let me just get rid of units. Okay, so what I want to do then is I want to graph in some way these estimates. So the original table, the velocities were 0, 1, 4, 9, 16. So that wasn't by chance. Those guys live on the t-squared curve. So what I want to do is I want to graphically represent the underestimate and overestimate. I'm actually going to do the overestimate first. The underestimate has something a little bit weird about it, which I'll show you guys in a minute. So what am I going to graph? So let's see, 1, 2, 3, 4. So I invite you to pause the video and look at these numbers, 1 times 1, 4 times 1, 9 times 1, 16 times 1, and think about this graph and think about a particular geometric object by which these guys are a type of measurement of. So pause the video for a second. All right, so hopefully you said, well, wait a minute, this 1 times 1, well, the 1 is the width here, this one is the width, and this one you could think of as the height on that function. And if I take 1 times 1, I'm actually getting the area of that rectangle. Similarly, 2 squared is 4. 4 times 1 is the area of that rectangle. 9 times 1, or 3 squared times 1, is the area of that rectangle. And 16, or 4 squared times 1, is the area of that rectangle. Interesting. Well, let's do it for the, this is the overestimate. Let's do it for the underestimate. And this one's a little bit weird. So the underestimate, it looks like my height is 0 for that first rectangle, and the width is 1. So this rectangle looks like this. For the second one, we're going to go up to a height of 1 and a width of 1. For the third one, a height of 2 squared, or 4, and a width of 1. And then finally, a height of 3 squared and a width of 1. This is the underestimate. So take a minute, pause the video, and try to determine what this total distance is also giving us. So hopefully you're seeing that by doing this problem that had to do with distance, we're actually now finding a way to approximate the area under the curve v of t equals t squared. So that should be a little shocking because we're now coming up with a process by which we can actually come up with the area under any function. And the way we do it again is we'll just take more and more of these rectangles. And that process will be fully cleared up over the next several lectures. All right, so this is an overestimate of the area under t squared and above, I guess, the t-axis. And this, once again, is an underestimate of the area. So I've mentioned a couple of times now that our goal is to take the number of subintervals and have that approach infinity, and to try to figure out what that would mean for us. So to get there, what I want to do is develop a mathematical expression so that I can have a formula and then derive results from it so that I can actually do that limiting computation. So let me keep those pictures up there. It might be helpful in a minute. But let's talk about this process in general. So if we want the distance traveled from t not, let me say A, which we're going to call T naught, to B, we're going to call that T sub n, we can break the interval into n sub intervals and add up each distance to get an approximation of the total distance. So basically, we're just going to add up the distances on each of these subintervals, and that would be our approximation. So this notation, t sub 0 and t sub n, might seem a little bit mysterious. And basically, what this is doing is we're adding a subscript to the t. And by adding a subscript to the t, it's making it possible for me to articulate as many subintervals as I want. So in this example, this guy would be t sub 0, t sub 1, t sub 2, t sub 3, t sub 4. So here I'm breaking this into 4 subintervals. If I just wanted to break it into 2 subintervals, I wanted to break it up into 2 subintervals. So for example, 0 to 2 and 2 to 4, I would call this guy t sub 0, this guy t sub 1, and this guy t sub 2. So those subscripts help me to articulate the various points. And I'm always going to use A to be the start and B to be the end. Let me also note that the length of a given subinterval is, well, I'm going to call it delta t for change in time. And now I invite you to pause the video and try to come up with a formula that involves A, B, and N. Well, hopefully you said it'll be B minus A, in other words, the length of the total interval divided by the number of subintervals. So that will give you the change in time. Well, how are we getting the velocities? We're getting the velocities by evaluating the function at the endpoints. And let's note that in this one, I use the right endpoint for each of these. And in this one, I use the left endpoint. So in other words, I use f of 1, 2, 3, and 4. Here I use f of 0, 1, 2, and 3. So we're going to differentiate these two by describing this guy as a right sum. In other words, I'm going to pick the rightmost endpoint for each of my y values. And this guy is going to be what's called a left sum. So before we go on, I have a question for you guys. It looks like the right sum here is an overestimate, and the left sum here is an underestimate. So my question is that always true? Is the right sum always the overestimate, and the left sum always the underestimate? Pause the video, please. Hopefully you said no. It's going to depend on whether the function is increasing or decreasing. Because if I did a right sum on a function that is decreasing, then I'm always using the smaller value for each of the subintervals. Similarly, with a left sum, if the function happened to be decreasing, function's decreasing, I'm always using the higher values when I do the computation. So that would give me an overestimate. All right, so back to the problem at hand, which is to try to get a general formula for this. So let's see. Let's do it for the left sum. See what we did up here. So it looks like I took the velocity of t naught, right? That's t naught. And I multiplied it by delta t. So that's taking my initial velocity times the change in time. Then I did it for t sub 1. So we have v of t sub 1, delta t. In fact, I did it for all the points, but we have to be a little bit careful here. I didn't do it for the last point. I didn't do it at b or t sub n. I actually stop short at t sub n minus 1. So this would be what the left sum would look like. So I'm going to give you a minute, see if you can come up with a formula for the right sum. So please pause the video and give it a shot. Well, hopefully you said here you're going to start at t sub 1. That's the first value that we used. So it would be v of t sub 1 times delta t plus v of t sub 2 times delta t plus dot 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 plus v of, well, here I actually go to t sub n because that's the rightmost endpoint. So I use v of t sub n times delta t. So this is what the formula looks like. Well, this is a little bit cumbersome. Again, my whole goal next lecture is to take the limit as n goes to infinity. And the way it's written is a little bit cumbersome. And I'm noticing that the structure of each piece in the sum is actually exactly the same except for the subscript. So we have special notation in mathematics that actually you'll definitely see in some of your science classes if you're taking science as well. And that's the sigma notation or summation notation. And the idea is this. What we'll do is we'll abstractly represent each of those pieces. So v of t sub I, so I'm using the variable I to represent 0 through n minus 1, times delta t. Then you just tell the summation where to start. So it's going to start at 0. And this symbol is telling me to take these guys and keep incrementing this subscript I until we get to the end. And the end in this case is n minus 1. So this is what it would look like for the left sum. And in general, if we have f of x, so in other words, this is if we're thinking total distance traveled, but maybe we want to think about just the area, and we don't actually have a velocity function. I could express this in x's as f of x sub I, with this, again, generic f function, times delta x. So let me give you a minute. Try to play the same game with the right sum and see if you can write out that expression. Right, hopefully you said that each of these guys looks like v of t sub I times delta t. And this guy is going from I equals 1 to n. So that would be the right sum. And finally, we can express that as f of x sub I times delta x. And sums of this form, by the way, they have a special name. They're called Riemann sums after a famous mathematician, Riemann. Right, so in this lecture, we introduced the question that we wanted to ask, which was, hey, how far are we traveling? And we proposed a solution. Namely, we can get the approximate distance traveled over each subinterval, then we can add those guys up. In subsequent lectures, we'll then take the limit as the number of subintervals approaches infinity, and then we'll try to find a reasonable way that we can actually compute that limit. All right, thanks so much for listening.